Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about goodness of fit. The idea is that a goodness of fit test is a hypothesis test that an observed frequency distribution fits or conforms to some claimed distribution. We have some notation. O will be an observed frequency. E is an expected frequency. K is the number of different categories. N is the number of trials. That is the observed sample values. And then we have a test statistic called the chi-square. It's the sum of the observed minus expected squared divided by the expected. All of this in the sum. The degrees of freedom is always k minus 1, the number of different categories minus 1. And this is always right-tailed. Let's do a quick example. The Fish and Game Department stocked a lake with fish in the following proportions. 30% catfish, 15% bass, 40% bluegill, and 15% pike. Five years later, they sampled the lake to see whether the distribution had changed. What did they have? So we have catfish, we have bass, we have bluegill, and we have pike. They caught 120 catfish, 85 bass, 220 bluegill, and 75 pike. So, did the distribution change? We'll use a level of confidence of 0.05. A significance level of 0.05. Level of confidence would be, what, 95%? The original distribution was 30%, 15%, 40%, and 15%. First thing we should ask is, how many fish total were caught in this sample? Let's see, we have 385, 405, 425. That's 500 fish. What is these are observed values. This is the percentages that we originally started with in the lake. What are the expected values? We expect there to be a 30% of 500 catfish. That's what, 150? 15% would be 75. 40% would be 200. And 75. So the chi-square statistic will be 120 minus 150 squared over 150 plus 85 minus 75 squared over 75 plus 220 minus 200 squared over 200 plus, well, 75 minus 75 squared over 75, but that's obviously 0. Let's see, 30 squared is 900 divided by 150. Then we have 10 squared, it's 100 divided by 75. And then 20 squared is 400 divided by 200. The chi-square that we get is 9.33 and so on. We can calculate the p-value for this chi-square distribution, which looks like this, by going to our chi-square, which was 9.33 and so on, and calculating the area from there outward. The smaller the chi-square, the more closely the observed and expected match. The bigger the chi-square, the less they match, the more the difference is. Which means that we can determine the probability that our null hypothesis, that the distributions are the same, and the alternative hypothesis, that they differ, can be found by calculating that area in the chi-square distribution. We can do that on our calculator using the distribution, second distribution. If we go up from here, the chi-square CDF, it gives us the lower value, which for us will be 9.3333 and so on. We want to go out to infinity, so for our upper, we'll just put something really, really big, like say 10,000. The degrees of freedom is the number of categories minus 1. We had 4 categories, so the degrees of freedom will be 3. So I'll punch that in, and we get a p-value of 0.025. That's less than our alpha, which was 0.05. So we reject the null hypothesis. And we find that the differences are statistically significant so that the distributions differ. But that's not the only way that we can do this. There's also built into the calculator a chi-square goodness of fit test. So I'm going to go to Stats and then Edit. The first thing I have to do is I have to enter these two lists. So I'm going to clear the lists that are in my calculator, and I'm going to type them in. The observed values were 120, 85, 220, and 75. The expected values were 150, 75, 200, and 75. So I've typed those in, so second quit. I'm now going to go to Stats and then Tests. If I go up from the bottom, there is a chi-square GOF, that's goodness of fit test. That's what we want. The observed values I placed in list 1 and the expected values in list 2. The degrees of freedom is 3, and so we're good to go. Notice it gives me the chi-square that we calculated before, 9.333 and so on, the same p-value, the same degrees of freedom. Everything's the same. And so once again, we reject the null hypothesis and find statistically significant differences to claim that the distribution has changed. The following problem is based on information from the National Oceanic and Atmospheric Administration, Environmental Data Service. Let x be a random variable representing average daily temperatures in degrees Fahrenheit in the month of July in Kit Carson, Colorado. The x distribution has a mean of mu equals about 75 degrees Fahrenheit, and the standard deviation is about 8 degrees Fahrenheit. A 20-year study, that's 620 July days, gave the following. We're going to have categories. In the first category, it's the mean minus 3 standard deviations up to the mean minus 2 standard deviations. And of those 620 days, 16 fell into this category. Mean minus 2 standard deviations to the mean minus 1 standard deviation, there were 78 days. Mean minus 1 standard deviation to the mean, that was 212 days. From the mean to the mean plus 1 standard deviation, there were 221 days. From the mean plus 1 standard deviation to the mean plus 2 standard deviations, there were 81 days. And from the mean plus 2 standard deviations to the mean plus 3 standard deviations, there were 12 days. We're going to test the claim that the distribution is normal. So these are observed. What we need are the expected. The way that we're going to do that is we're going to find the area under the normal curve with these different regions. Mean, mean plus 1 standard deviation, mean plus 2 standard deviations, and so on. Between here, the mean and the mean plus 1 standard deviation, we'll get an area. We'll multiply that area, which is a fraction between 0 and 1, times 620. And that will give us the expected number of days within that category. I'll put the expected over here. We can find the necessary areas by finding these areas under the normal curve. From 3 standard deviations less to 2 standard deviations less, what is the area times the 620 days? What we'll do is we'll look at the second distribution, and we'll go down to the normal CDF. The lower will be -3, and the upper will be -2 on the standard normal curve, so the mean of 0 and standard deviation 1. If we take that and multiply by 620, that should give us the expected number of the 620 days that lie between 3 standard deviations and 2 standard deviations from the mean, below the mean. And so we're getting 13.27. How many between 2 standard deviations and 1 standard deviation? We'll do the same thing. Second distribution, normal CDF, but this time from -2 to -1. We'll again multiply by 620, and the expected number is 84.26. Between 1 standard deviation and the exact mean, we'll go to second distribution, normal CDF. -1, 1 standard deviation below the mean, and the exact middle, the mean. We'll multiply by 620 once more and get 211.63. Now the distribution is exactly symmetric. Between -1 standard deviation, 1 below the mean, and the mean, you get the same thing as from the mean to 1 above. And so this should also be 211.63. That makes the next category 84.26, and then the final category 13.27. We need to put all of this data into 2 lists. So doing that, we'll go to Stat, Edit. We'll clear our lists and type 16, 78, 212, 221, 81, and 12. 13.27, 84.26, 211.63, 211.63, 84.26, and 13.27. Second, quit. We'll now go to our stat tests, and we'll go up from the bottom to the chi-square goodness of fit test. The number of degrees of freedom, we have 6 categories. So the degrees of freedom will be 5. And we find then the p-value and the chi-square value. Chi-square is pretty small, 1.690. And the p-value, which really tells the tale, is 0.89, which is way greater than our alpha, which is 0.01. Because the p-value is so huge, we fail to reject the null hypothesis. The null hypothesis was that the distribution was normal. So we do not find statistically significant evidence to support the claim that the distribution is not normal. We fail to find statistically significant evidence that the distribution is not normal.